Yeah, I guess we'll just go ahead and get started here. Welcome
Okay.
to our final review of the MapGen uh, generator project, displayed by Michael Fiano and Elijah Malaby, who's been helping out with a lot of the McClim-related issues. I'm your host, Ram Vedam from Atlanta Functional Programming. For those of you who are interested in the live coding session that was performed yesterday by Michael Fiano, the entire 5.5 hour live coding session is available in its entirety. I will post the URL in the comments. It's also going to be in the basic information of this live stream URL once the YouTube recording is completed. So if those of you who are joining in right now, watching on our live stream channel, you should see in the description eventually the YouTube URL to that live coding session. And so without further ado, Michael, take it away.
Hi, thanks for joining us for the final installment of our map generator workshop. This weekend we worked on it and actually finished up the map generator. Where we left off was on...
we just carved the corridors, I believe.
Yeah, step 3. We finished step 3. This weekend we did, the last 3 steps. The first step we did was connecting the regions. If we look at image, let's see. Okay. When we draw the map, last week we left off. Did we do the corridors last week or no?
We drew the rooms,
yes.
But I don't think we drew the corridors.
We had the corridors at the end of last.
Oh, no. I think we did the corridors on Saturday. Actually,
yeah, we did the corridors on Saturdays.
Yeah. Oh well.
Last Monday we just did the rooms. We didn't do the.
Yeah, I'm pretty sure we did this one step on Saturday and these 3 steps on Sunday.
Yeah.
Oh yeah, we might have. Wow. I forgot how much we did this weekend.
Okay, so let's start over here.
Yeah.
When we left off last week, we had something that looked like...
You actually passed the image.
Right here.
Yeah, right there.
This one. We randomly placed rooms onto our stage. The dark area is solid wall, and these are just rooms, square rectangular rooms. And the next step of the algorithm is to take the empty space and start drawing a maze algorithm all around the empty spaces until it can't draw anymore. It might get locked in. Therefore, we look for more empty spaces, and we start drawing another maze algorithm until the whole stage is filled with mazes, and it looks something like this. That step is what we did Saturday, and how that was step 3 of the algorithm. We draw maze algorithms, repeat until the full map is filled in with rooms and mazes. Now, when we originally drew the rooms, they have their own region, which is implemented as just an integer. Like the first room is region 1, etc. If there's 10 rooms, there's 10 regions. Now, when we first start drawing the corridors in between the rooms, they start at the next region ID. So the first corridor would be 11, and so on. So basically, every distinct region has its own unique integer, and that's important for later when we connect the graph. So let's walk through the corridor code. That's the first thing we did this weekend. So let's see.
Yeah,
everybody see my screen good?
Yeah, fine for me anyway.
Okay. So this is our main stage file here on the right, where we're implementing all the steps of the algorithm. We have the first step: make grid, carve rooms, carve corridors. This is where we started this weekend. Carve corridors is the top level function for the 3rd step, and that is in our make stage function, which calls carve corridors in our corridor file. Where is it?
You just passed it. There it is, right there.
Oh, okay, right here. So yeah, just like, is that just like rooms? No.
No, rooms do something different, I think.
Did we use convolve before?
I'm not sure if we've used convolve yet.
We haven't talked about convolve really in detail, I don't think.
Yeah, you're correct. Okay, we only use it in 2 places.
Yeah. So if we can go and start with that function, that would probably...
Sure.
Okay.
Yeah.
Okay, so last week we briefly glossed over the kernel code, which does image-based convolution maps, where we're creating a kernel, which is a window over a cell on the map. So if we have this cell and our kernel is a square 3x3 kernel, we're looking at these 3 cells all around or these 9 cells, 3x3 area, all around our origin cell in the middle. Now a kernel in our library here doesn't have to be a square. It doesn't even have to be a rectangle. It could be, a plus shape, or it could be anything. And that's what our kernel code is doing, is it's creating a window around a cell that we want to look at on the map. Now, in order to carve the corridors, what we have to do is we have to create where is it? We create a rectangular kernel. That's what this layout rectangle means. And we're convolving over the stage. This convolve function, what it does is it loops over every cell of the stage, starting on the inside. It ignores all the border pixels, basically. And
people are getting a little lost.
Yeah.
Okay.
So
you say people, but it was just me.
Where should I? What
it's my fault, to be fair, because I was trying to get my friend to join, so I wasn't paying attention. I'm sorry.
Okay.
So could you just do you have a specific question? I mean, that's a...
No.
Okay.
Well, yes, I do actually. The kernel, what is that?
So...
Yeah, go ahead, Elijah.
The kernel itself represents... It stores a location and an extent, which is just sort of the minimum and maximum distance away from that origin point, and a pattern, I guess you could say, a shape, which describes the cells around the origin point, which that kernel is sort of active for, right? And the idea being that we can then do operations on those cells which are adjacent to this origin cell after we've created that kernel centered over that origin cell.
I understand.
And so a rectangular kernel is just one that you give it your maximum x radius and your maximum y radius, and it creates it grabs all of the squares that are that many steps in x and that many steps in y away from your origin square, and then you can do something to all of those squares or to some of them, right? And so convolve takes a layout, which is another way we've called that is it's a kernel factory. A layout is a function which takes the stage and in origin position, it produces a kernel that's centered, and centered over that origin position. And the idea is that when you say layout rectangle, that creates such a layout function, function from stage and position to a kernel, such that the kernel it creates is rectangular. And you can also give extra arguments to layout that define things like the radius and such, but the default radius is 1, and that's all we needed there.
Right. Okay.
If that makes sense. The layout is just a way of making a kernel centered over spot.
No, I understand. Get it.
Yeah. And so convolve there, it goes over every single cell of the stage. It instantiates your layout on that cell. Then it passes, to get your kernel, and then it passes that kernel to your filtering function, and then if your filtering function says, returns true, it passes your kernel to the effect function, which actually does something with the cells at that location or the adjacent cells.
Right, okay.
Yeah, a kernel is just a window. I mean, the best way to think about it, say you had like a piece of graph paper, and you had a colored piece of glass with a square drawn in right in the middle of it.
No, I understand.
The shape of that glass is the kernel. Only what's under, what you can see through the glass is what the kernel can see. It just, you know.
It's related to the function you were saying you needed to rewrite the other day or trim down yesterday.
Yeah, that was involved in kernel stuff. Yes.
Because that found the other surrounding blocks, didn't it?
Yeah.
Yes. So what convolve is doing is it's mapping over the whole stage, creating a kernel for each shell of the stage, looking around at its neighbors, and doing some filtering based on the state of the neighbors, whatever filter function we want to pass to it. If that filter function passes, then it runs the effect function. That's all it's doing. It's just it's looking at the status of all the neighboring cells that it wants to look at, and it runs some effect if that passes true. And the way we do it for carving the corridors is, we map over the whole stage with a rectangular kernel, and we run the filter carvable. If filter carvable returns true, then we run the effect carve corridor cell. Now, what filter carvable does is, that's your new function, Eliza. Here's where you take it away.
Yeah. So Kernel Detect, it's actually a rather simple function. What it does, so we have kernel map, right, which is basically it applies a function to each cell that's accessible by a kernel, and then it collects the results of that function into a list. We also have a function called Kernel Detect, which is similar to kernel map, except instead of actually collecting the results of all of the calls, what it does is it sort of takes a predicate function instead of a mapping function. And any time that predicate function returns something truthy, something non-nil, it returns that value that the predicate function produced immediately. It doesn't go any further, right? So the idea is that if our function there is carved p, right? Basically, if the moment it's going to call carved p on each cell visible by the kernel, because that's how kernel map works. And then when the value returned by carved p is true, it's going to immediately return that true without checking any further, right? And so
it's simple. It's just checking the feature slot of our cell object.
If it's a wall.
Whether it's wall or not.
Yeah. And so, kernel detect there, it's a little tricky. If you see that there, we define a block which allows us to do an early return, basically. And we do kernel map, and then the function that we're actually mapping over there, takes each cell one after another. It calls our function on the cell, gets the value back. It uses when let there, so it knows if the value is truthy, and when the value is truthy, it returns it. And since we named it a nil block, that return hops all the way out of the kernel map, hops all the way back out to the kernel detect.
And so when let only it only works when that's true.
Right. Yeah, okay. When let. It does a let, and then it does when. Do you mind macro expanding that one, Michael? It's pretty simple.
Yeah, I have to start my image. Hold on.
Yeah. And you might have to reload that buffer, revert the buffer. At least I do when I start my image after I...
Yes. Yep.
It's a lot of warnings right there.
Yeah, he has verbose turned on in his quick Lisp. Space B, Shift R, by the way. Or it might be space, yeah. But yeah. So it literally just when value...
That's the expansion right there, the highlighted area.
Oh, okay. Oh, all right. Oh, okay.
It's a nice little convenience so that you don't have to do the let block before writing the when.
Yep. The reason what the and is there is because you might let multiple values or multiple things, and then it needs to know if they're all truthy.
Yes.
But yeah. So anyway, it's a pretty simple function. And then if you note there, right after the kernel map, we have that nil, so that if the kernel map does return, we throw away its return value and we return nil. Which is a little silly, but it does the job.
Yeah.
But yeah. So that's just a way that we can quickly detect for a value in one of the cells that our kernel can see, right? And this way, filter carvable, it's determining if the cell that we're on makes sense to carve as a corridor, and so the way that it does that is it has a little 3x3 cell, or a 3x3 kernel, and it checks to see if, any of those cells are carvable, or carved already, sorry. If any of those cells are already carved, and when none of them are carved, we know that this is a valid cell to turn into a corridor. And the reason for that is we always, we always need to maintain a one wide wall everywhere. So
yeah, so basically, if we're right next to a room here, and we're looking at the kernel around it, we see that these two are already carved, so we can't start carving a corridor here, because then it'll be part of the room, basically. We need to start here, where there's all wall all around the pixel we want to start carving at. And that's what that's doing.
Yep.
Mm-hmm.
So, yeah, the maze algorithm, was there a question? Go ahead.
Yes, you have the when let, right? So the when let, yeah, okay. This is, in the grand scheme of things, this isn't very important, but it says you have when let value funcal, so it will, that if value is something, it sets it to the value of that, right? What?
Right. Well, the important bit there is that return, right? Which is hopping all the way back out to our block.
It's mapping. Okay, yeah, I understand. Yeah, I see kernel map. My bad.
But yeah.
Everything is fine. It's cleared up. I cleared it up.
Oh, good. Anyway.
Okay, so where were we? Yeah, that's our filter for our carve corridors function. Remember, if this passes true, if the filter passes true, then it runs the effect, and the effect is carve corridor cell, and that's going to do all the heavy lifting of actually starting the maze algorithm. Right here. So this was something that you refactored, Elijah. You want to go through this one too?
Oh yeah, I rewrote that one to actually be tail recursive.
Sweet.
So, but basically, the idea there is that we want to let's see, how does that work again? Right. So we so select there basically lets us translate from kernel coordinates back out to stage coordinates. So select kernel 0, 0 gets us the cell at the center of our kernel. Make region basically just increments our region counter. So anytime we carve a new cell,
it assigns carving a new corridor.
Well, yeah. Every time we call carve, it applies the current region, and make region just increments our region counter. That way, it's pretty simple for keeping track of what region things are in. So we carve that origin cell as a corridor. And then the idea is that we want to basically spread out recursively across the entire map, right? Trying to fill in the entire space. It's a maze drawing algorithm. We get our stage out. We get a layout there, which is an orthogonal layout, which is important. That makes it's a plus shape, and our radius in both directions is 2. So it's actually it's really 5 wide and 5 tall, and that lets us step out in either direction by 2, which is important because we're maintaining this sort of we operate sort of on the odd cells everywhere, which allows us to maintain that we have 1 wide walls between everything. And so then we have our tail recursive function there. It's important to sort of see that we give it a list of cells, right? And we use choose corridor cell there, giving it our stage and our list of cells. That gets us, it picks one of those cells. Then we form a kernel, using our layout that we define there. That puts that plus shape over that cell. And then we pick yeah, we carve. Oh yeah, carve direction. That one I didn't write. But basically, carve direction produces a new list of cells.
Well, we got two new functions in here that we haven't talked about.
Right.
Corridor cell and the choose direction.
Right. So let's look at choose corridor cell and carve direction.
Okay. Choose corridor.
Yeah. So choose corridor cell.
Cell. Okay. So what that's doing is it's Oh, that uses one of the user options. Okay.
Yes. So we've added a few more user options.
Whoops, put too much. So if we go to our options file over here on the right, we have a bunch of user options in our options class. We added wild factor here, which is a poorly chosen name, but what it means is it's how. Wait, is that what we're using? Yeah, wild factor. It's how windy the corridors are going to be between the rooms, whether they're just straight or mostly straight or very, very windy. It's how wild the corridors are, basically. And what we're doing is we're choosing a random float right here. And if that's greater than our wild factor, then we...
Could have used random bool there. Huh. Don't know why I didn't notice at the time.
Yes, we could have. But anyway, we're using the maze algorithm called recursive backtracker. It's just one of many maze algorithms. And it has the property that if you choose a random cell, a random direction to carve in, it's going to create a more random looking maze rather than, have a bias in any direction by choosing the first or the last cell or a specific index each time. Choosing a random element is going to cause the maze to look a lot more random and have less of a bias.
Yep, so it causes the corridors to become more windy.
So the more our wild factor is, the more windy our corridors are going to be.
Yep.
That's what that's doing, and yeah, that's what we bind choice to here. Wait, is that what we were looking at? No.
Yeah.
We were looking.
Yeah. Then we have carve direction. Yeah. So choose corridor cell there. It's got that list of cells, and it's getting out. It's picking one of those cells. It's either picking the first one or a random one, depending on how meandery the user wanted things. And then we're centering a kernel over that cell, and then we're carving in that direction, passing the list of cells in. So let's head over to carve direction.
Okay.
So carve direction there, once again, it pulls out that origin cell. It picks a corridor direction. So let's look at choose corridor direction. That these are both your functions, Michael. So
okay, so let's see. Sensitive keyboard. I got a new keyboard today. Carve direction. What that's doing is okay. So carve direction. It's first. It's looking at the origin of the kernel that we passed into it. The cell right in the middle of our kernel. It's choosing a direction from that cell, which could be left, right, top or bottom. And that is calling out to this function to do that. It's basically looping over every direction as an offset vector, 0, 1, 0, -1, etc. And whatever direction, actually, it's iterating over those directions, and then it's creating a...
It's coming up with a list of the directions that are legal to carve in, because we need to know that if we go 2 cells out, there isn't something already carved there, because we have to carve in increments of 2.
Yep. Okay. So yeah, it's creating 2 cells, both in the same direction. So say it's right. This would be 1 to the right of the origin and 2 to the right of the origin for this one. And then it's checking if cell 2, the one farthest out, is carved or not. If it's not, it's pushing both cell 1 and cell 2 to this empty list up here. and then it's choosing a random one from that list.
Yep. It's pushing the pair cell 1, cell 2 onto there. So what we'll end up with results will be a list of those pairs of cells, right. And then random element is going to pick one of those directions to go in, one of the valid ones.
Yep, and both of those cells are returned because we're pushing a list of cells, and both of these cells are going to be the ones that are carved. We always have to carve 2 at a time, and that's just to maintain our odd. Everything is odd based in our map. We always need to carve in 2 cells at a time when we carve the corridors.
So then, carve direction there. It gets that choice of direction back, and then it goes through each of those cells and it carves both of them, carves those 2 cells, and then it pushes both of those, onto the list of cells that carve direction is passed in. Carve direction is passed a list of cells to sort of backtrack to, in a sense, and then it pushes the second one. It doesn't push the first one. That's why that's in the finally.
Right.
Because we only want to push the odd ones back onto cells. And then after we've done that loop, we take our origin cell and we put it on the list of dead ends.
That's not after the loop. That's if that's.
Oh, right. The alternate path. Yeah. Right. If there was nowhere to go, basically. If there was no direction that choose corridor direction produced, then we mark
the dead end, so we have to mark our dead end for a later step in our algorithm.
And we remove that cell from our list of cells. Either way, push there returns the list it's given after it's pushed the thing on, and delete also returns the list. So this function, it takes a list of cells that we might, want to explore from in the future, and it moves it forward, from the one centered at our kernel, and it, then pushes the new cell that it explored to onto that spot. And so then later on, we're back in carve corridor cell, right? The idea is that since carve direction produces the new list of cells, right, either by pushing the cell that's 2 further along onto that list of cells and returning it, or by deleting the cell we were on because it was a dead end. We then basically, recursively invoke our function on the new list of cells so that, as long as there are cells to go to, we pick one, either the first one or one at random, in choose corridor cell. We make kernel centered there, and then carve direction, we'll move 2 cells out from that cell, right? And or if it can. And if it does, it pushes the new cell onto the list of cells and returns it, and otherwise it, marks that cell as a dead end, and returns a list with 1 fewer cells. And so the idea is that this will branch out over the entire accessible space from wherever origin cell you started at, and it'll eventually mark a bunch of dead ends and fill in every single possible location where it could put a corridor. Is the idea.
Yep.
So does this make sense to everybody?
No.
The silence.
No, it makes sense.
Well,
but then again, I was involved. I was there when this was written, so I have an idea of what you guys are doing.
What we could do is we could visualize what it does from last week, I guess.
Might be a good idea just to show what that stage. I don't know if you can actually show different stages.
We can show individual stages in principle. We'd have to modify the make stage function.
Okay, so we could.
I think if you get rid
comment at everything, Pat.
Yeah, comment.
Comment at everything after carve rooms. Why are you using space C?
That was my other keybind in my other program. Other editor. I forgot what it is. What's the comment operator?
Semicolon.
Okay. Any editors? Okay, so this is where we were last week. Okay.
We had the rooms.
Yeah. We had a bunch of rooms carved. That's probably really small for you guys. Hold on.
It's not that bad, actually,
Yeah.
although it's hard to see the grid.
And I changed the renderer. Oh, actually, that is
Yeah, that's actually plenty big.
what it was last week, I think.
Yeah.
So yeah, we have a bunch of rooms.
Not really much better. I mean, it depends on what you
changed the. I know what we had to do last week.
We had to change the width of the line color. I think.
Yeah. So let me.
I mean, we have to change is the number of pixels.
Yeah.
That it's down by.
I know what to change. Let's see.
Yeah.
The
Draw a rectangle.
draw right here. Changed it to 4 last week, I think.
Yeah. Of course, this is going to mean the circles won't be properly centered anymore. But oh well. Don't worry about it yet. We'll get there eventually.
Everybody see that?
Yes.
Yeah.
That's very clear.
Okay, yeah, I can see it on my computer. So yeah, we have a bunch of randomly placed rooms. That's where we left off last week. This is the step we just talked about, the carved corridor step. If we uncomment that, and
Just click, I suppose.
no, I want to do the same.
Oh, yeah.
That's what it does. You know, it's just it carved. This is not a very good example because we don't have a densely packed room, so it's all one big corridor.
Yeah, make it smaller and increase the density, if you don't mind. Be easier to see, I think.
Oh, that's still not very dense. Turn it all the way up.
Yes, all of the density.
Yeah, we can clearly see a distinct corridor right here. A few of them.
Right. So it would have picked one of the cells, you know, say for the upper left corridor, or it would have picked one of those cells as the starting one, probably the one in the most upper left. Although I'm not entirely certain how Sketch's pixels map to our internal coordinates. But it would have picked one of the corners. It would have started there, right? It would have discovered that it is a carvable cell because that's what our filter does. And then it would have hit carve corridor cell, which would have actually carved that whole corridor. And I'm now realizing that might be a rather poorly named function. But anyway, so carve corridor cell carves an entire corridor. As misleading as the function name may be.
What's funny is we actually renamed it from carve corridor to carve corridor cell.
Oh well,
what we were thinking, but we did.
Yeah, that's silly. But anyway, so it would start at one of those cells, right? And it would maintain a list of cells where it can explore further from, right? Cells where there are additional locations, I guess you could say, to branch the maze out from, right? And so it starts at 1. It starts branching out in increments of 2, right? And it each time it goes through carve corridor cell, that recursive function there. At each step of that recursive function, it's picking one of the cells that it thinks there's still a direction it can expand out from there. It's picking one of those cells and expanding out from there by another 2 cells, right? And then it's recording that new cell in the list of cells that it can expand further outwards from. And the idea is that if we have a bias towards the most recently explored from cell, right, which would be the first cell in the list, because each time we explore a cell, we push that cell back onto the front of our list. Or each time we explore the new end, the new furthest edge of our corridor, we push that cell onto the very front of our list. And so if we have a bias towards picking that first cell, we'll have a bias towards, expanding the most recently explored corridors out further and further in a line, which, makes the whole thing much more linear instead of more like a tree. It's like, it's more of a depth first search instead of a breadth first search, if you will. If we bias towards picking the first cell and expanding from 2, and then picking, that new first cell and then expanding 2 again from there, as opposed to, picking a random cell each time from our list of cells we could explore further from, which would produce something more like a breadth first search, if that makes sense to people. And would produce a corridor that looks a bit more like a tree. So, Does the visual aid help a little? I don't know. Understanding the map algorithm is a little tricky, I suppose. People are being quiet. But anyway, so that's corridor carving. It's we picked a map algorithm and implemented it. And the convolve step. The convolve step is really just to make sure that we fill the entire map with corridors. We aren't actually going to be generating corridors from like every single cell. In fact, most of the time, convolve is going to be skipping over cells because there'll be cells that would have been carved by previous corridor carving phases.
Yep.
So convolve is going over the stage, and it picks the first cell, and then it generates as much of a corridor from there as it can, and then it'll start scanning across cell by cell by cell, and for the most part, it'll find that these cells are already adjacent.
I'm gonna throw a spanner in the works right here, and,
sure,
and show my lack of understanding.
Sure.
But the blue rooms that you made.
Yes.
When did you make them? Obviously, you were making them before your...
Right, so that was an earlier week, was our carve rooms stage.
Yeah, this is the third and final week of our algorithm here.
Okay.
We did work on this the last 2 weeks as well.
Yes.
Those
I wasn't here last week. So.
Yeah, it's all up on YouTube.
It last week,
yes.
But the actual coding session that you saw yesterday is not recorded.
Right. We didn't actually record coding the rooms.
If you want to go up to our YouTube page, it's Atlanta Functional Programming.
Yeah, is that another? Is it an algorithm that you use to randomly generate those rooms?
I suppose we could take like a minute or so and just look back over that for people who
Sure.
Ring.
Whose phone is that?
Rooms. So, our stage function file is calling carve rooms.
Right.
What carve rooms is doing, the first thing it's doing is it's going to take an estimate of the room count that it can make.
Yep, and that's just a heuristic. Yeah.
Given the width and the height of the stage and how dense we want to make it, we're just going to take a guess as to how many rooms we could actually generate, given those dimensions and constraints. And we're gonna check first thing we're gonna do is we're gonna loop until we reach that estimate. Okay, as soon as that estimate hits, we're gonna exit out of the loop. Or if we reach 500 failures. And the way this works is it's gonna each time it's gonna try carving a room. And carved room is here you go, Elijah.
Yeah.
I don't want to go through this, and this took like 20 minutes just to explain last time, and I didn't do a very good job of it.
Yeah. I mean, it, so, basically, we have a center cell for, the, room. Generate room properties there basically comes up with a place where we might center a room. X, Y, width, height. Where X and Y are basically they're more so that we take half of that so we get radii, and then we can make layouts which use those radii to construct a rectangle around our center point. And so layout there is taking its max X and max Y, which are the X radius and the Y radius. That way we're making a rectangle that's exactly the size of the room. And then, we make another rectangle which is one size further out. And then what we do is we make absolutely certain that none of the cells in that larger region, one size further out in our room, have been carved. And that's just to make sure that we maintain the wall around the edge of our room. And if so, we make a new region, we just increment the region counter, and we go through all of the cells that are actually in the room, and we carve them out. So it's not too complicated, but it's using our kernel system pretty effectively there.
Yep. So, basically, when we carve a room, we want to make sure that every cell around the room, all these dark gray areas are actually dark gray areas. We do not want to carve in the middle of a room.
Right. We don't
want rooms to be touching each other.
Right.
So that's why we create a kernel, which is one cell larger than the room we're actually going to carve, and then we carve, the smaller kernel, the inside of that big kernel. The larger kernel is our test, and the smaller kernel is what we cut out.
Yep. And generate room properties just comes up with a random position and size based on the options the user gave. It's not terribly interesting.
So, little side question here. This every null is
that's
kernel detect.
that's a not kernel detect.
Yeah.
We want to actually modify that.
Be consistent.
Well, not kernel detect.
Yep.
Yeah.
Unless.
Sure.
Yeah, you could use unless. That's probably better. Yeah. Sorry about that earlier.
Okay, so yeah, that's all room carving does. That's the whole file. Well, we didn't talk about generate room properties, but that's all that's doing is it's generating, it's generating an odd-shaped room at an odd position in the stage.
Yep.
It can't start at 0 because 0 would be the edge. We want to border around our whole stage of walls. So it starts at 1, and it just picks a random.
Yep, and we always want rooms to be centered on odd coordinates because it just keeps the rest of the math in the system a lot easier to maintain.
Yep. And that's the whole file. That's all room carving. It's really just rectangular intersections. That's all it is.
Anyway, so we've carved the rooms, we've carved the corridors, and now is the time for junctions. Right? Yeah.
Connection of regions, yes.
Yeah. Oh, right, yeah. Connecting regions, right. Connectors.
If we jump back to our org file.
Right.
Excellent.
Yeah, and this is starting the stuff that we did yesterday, which we actually both streamed and recorded. So if you guys are interested in watching us try and put together the code for regions, junctions, and uncarving, you can see that.
Once again,
yes,
I did post the YouTube URL to your video. It's in the actual basic info of the this video. So once the stream is stopped, it should have all the information for them to get access to that guy.
Yeah, it's quite a lot. I mean, you must have a lot of free time on your hand if you even bother watching it. It's about 3 hours. It's about 3 hours of me fumbling over my keyboard and about 2 hours of Elijah extending his renderer. And about 30 hours of just us, wondering what we're doing, I guess.
Yeah, well, it's only 5.5 hours long, but we somehow managed to cram much more time of us being confused than we had any right to.
The contact to noise ratio is very low.
But yeah. Anyway, so connecting regions.
So what we're going to do is, if we go back here, I don't have it.
Yeah, let's just render it. Just render one with regions, with regions connected. There we go. So basically, connectors are all those little yellow dots there, and they represent places where two regions are both adjacent to a given cell. You have two distinct regions, either above and below a given cell, or to the left and the right of a given cell. And so basically, those are places where we could reasonably put like a doorway or a door and connect two regions together.
Yep. The first thing to note is that connectors can only be on a wall, so they're always on the dark gray areas here. And yeah, like Elijah said, a connector is only placed if the cell on the top and the cell on the bottom are two different regions, or if the cell on the left and the cell on the right are two different regions.
Yep.
That's all a connector is. It's a wall cell with two different regions on either side of it.
And the logic for that's actually relatively simple. I think this was the one that took the least amount of time to implement.
Yeah, it was the one after the step after that took a real long time to.
Yeah, carving junctions took a while.
So connect regions is our top level function, and it's right here. It's also using convolve.
Yep. This time with an orthogonal layout, just because we only need to look at the cells that are within a plus area. Although, yeah.
Right. It's not legal for a connector to have diagonal.
Well, it is legal. It's
well, it is legal as long as
we don't check for it. We don't care really about the diagonals.
Right.
Because you can't move across a diagonal in the particular geometry that we're designing this dungeon around.
Right.
And so it doesn't matter if things are diagonally adjacent.
And it's using convolve, so it's going to map through every cell, checking a filter for each cell, and if that filter passes, it's going to run an effect for each cell. The filter is filter connectable right here. It's doing exactly what we just said.
Yeah. Make sure that we're on a carved cell, and then,
it's making sure that we're
not
carved cell.
Right. I get those mixed up so much. I don't know why. Make sure we're on the wall.
It has to be a wall. That's what this means. Which we could have just used feature present p, but okay.
Yeah, but this is easier to read.
And either or of top and the bottom or the left and right must be two different regions. Cell regions distinct p is checking that, and that is just.
It's a little complicated because we generalized it for an arbitrary number of cells in there, even though we didn't need to.
Yeah, I don't know why I did that, but
it gets the job done. So we go through each of those cells, we get its region, we remove the 0 region, which is the region that we put in there sort of as a default, right? It's the region everything starts out in. It's what all the walls are in as well. So that gives us our list of the regions of those cells that we're trying to determine are in distinct regions. We make sure that after removing all of the 0 regions, we still have at least 2 cells to compare, because if we only have one cell, while yes, technically a single cell is always in a distinct region, it's also not really distinct with respect to anything, and so this function returns nil if, after removing regions, we only have one region left. And otherwise, we apply the not equal function there, which tells us that all of those numbers are different. So, not a too complicated function.
That's all the filter is. It just, checking the top and the bottom or the left and the right for 2 different regions of a wall cell. And then it's going to call make connector if that passes true. Make connector is all it's going to do is it's going to add this connector to the cell features list.
Yep.
Regions. Oh, okay. And it's also going to push that cell onto the our region state hash table.
Yes.
And that's needed later because we need to know what cells are part of which region.
Yeah.
Rather than have the reverse where we're just
right. So we once again we pull out the regions. This time using kernel map, so we just get out all of the regions that are adjacent to the cell. We remove the 0 region again, and I just realized that we probably should have removed duplicates from that. I don't think it actually matters, but we probably should have removed duplicates from that.
From which one?
From the list of regions coming out of kernel map. Because that could potentially return 4 different regions. In fact, it will return 4 different regions. I think for all practical purposes, I don't think it's possible for there to be a place in our map where there are more than 2 regions adjacent to a given wall. I don't think that's something that our map can actually generate the way we've constructed it so far. But, technically speaking, that does look at 4 cells. I don't know.
What is regions returning here? A list?
Yeah, it's a list of the adjacent regions.
Oh, a list of kernel map over region. Okay.
Yeah. I'm pretty sure that there will only ever be 2 non-zero regions in that list, and so remove 0 there works fine. Just because of the way we've constructed the geometry of our dungeon. But strictly speaking, I think that's fine. I don't think that'll actually ever cause an actual problem. It just looks a little weird to me.
I'm interested in looking what this actually.
Well, it should only ever just be a list of 2 regions.
So what about remove duplicates then?
That would only matter if there could ever be a situation in which there were more than 2 non-zero regions adjacent to a given cell, and I don't think that's possible just because of the way we've made the geometry of our map. Like, if you look at the map, just because of the way that the map works, I don't think it's possible for there to ever be a case where there are more than 2 regions adjacent to a given cell that are non-zero.
Right.
Technically, that kernel map is looking at 5 cells, but the center cell is always going to be in the 0 region because we make sure it's not carved. So I don't think it's actually an issue. It's just in principle.
Yeah, and that's all. Make connectors very simple. It's just marking a cell feature, and then our renderer just draws it a different shape and color.
Yep. And we record that that cell is in that hash table, which goes from, it's a hash table that maps from the, that's the regions table, the connections table. Yes. See, so we have those pairs on the left there, which are the 2 distinct regions, and we have a list of cells which ended up registering as connecting those 2 regions together.
Interesting.
Yep. And that's important because it affects how we later compute our minimum spanning tree when we get to the next step, which is carving junctions. But yeah, so figuring out the connectors is the easy bit. It's just, going through all the cells and checking.
Yep, and that's all. That's actually all of the 4.
Yep. Then we carve the junctions, and that's where it gets fun.
Yeah, that's.
Yeah. Do you want me to keep explaining? I don't know. Either way.
I think you're good. I mean, you're doing good. I spent 5.5 hours talking about it yesterday, and I didn't do that great of a job. So.
Well, you were also writing the code as you were explaining it, so changing into your feet. But anyway, so
functions looks like.
Yeah.
Hold on just a second, guys.
Yeah, I think you forgot to save the color change. We've got the door color still the same.
Yeah, the door color is the same as the room color, which is just confusing.
Make it brown again.
I'm just going to make something up here. Whatever. That's got to be different.
Oh, well, set up.
I almost did baggers.
The amount of time he's lost on that stream trying to figure out why his def files don't update things. Anyway. It's so easy to do, though.
Oh my god, that's so close to what we had, too.
Let's do 0. Yeah, just make it green.
And I just did it again.
This is why I use def parameter, but there are good reasons to use. Yeah. So basically, carving junctions is about figuring out some of the connectors and actually picking them as the ones that we're going to make doors or doorways out of is the idea. Actually, can you make the junction color also be that?
Yeah,
since we do this differently, connector color, because we don't bother.
Connector color is different.
Oh yeah,
make it the same color. I think that would. Have
to.
Oh right, yeah, because we just do that. Yeah.
So if we go, that's a T. Okay.
Just do an OR, yes.
Well, OR is easy. We just we use feature intersection. But anyway, yeah. So let's just make the junction color the same as the door color for now. We'll change it in a minute, maybe as we need. But for now, we'll just make them the same.
Okay.
Okay.
We're gonna have to reload this, right?
Nope.
It's live.
Yes.
That's why it's so slow. That's why it's so slow, because it's reading our map structure for every cell, for every frame.
Yeah. Anyway, so So all those pink squares there are places where we've turned connectors into junctions. We basically pick them, and the idea is that first we want to pick, the minimum number of connectors to turn into junctions in order to make sure that every single location on the map is reachable by some path, even if it's a really long one. We want to pick the minimum number of connectors required to make the map connected. And then we add a couple of extra ones so that we have some, because if we do the actual minimum, there'll be one path to any given location. But we actually want the map to be a little more interesting than that, so we allow, in some cases, to add additional connectors so that there are some cycles, so that there are additional paths to get places, etc. But basically, the idea is just, so the trick sort of comes down to, well, how do we figure out the minimum number of connectors to turn into junctions, so that we connect the graph, and the way we do that is with computing the minimum spanning tree, right? For those of you that know any graph theory, this is where the graph theory comes in. Basically, each of our regions can correspond to nodes on a graph, and each of our connectors are they're similar to edges, although there are a lot more connectors than there are actually edges, because each connector that connects the same two regions together, really they all count for just one edge in our graph. But the idea then is just that once we construct some graph data structure that describes the way that each of our regions are connected to each other, we can compute the minimum spanning tree of that graph, and then we know which regions, really, all we know is by the edges of that minimum spanning tree, we know which regions must have connectors between them that we can turn into junctions. And if we pick one of the connectors that is set up to connect those two regions together, if we just pick one of them, then for each of the edges in our minimum spanning tree, even if we just pick one connector that corresponds to that edge in our minimum spanning tree, that will connect those two regions together in that same way, and that way it'll connect our map entirely. For those of you that know any graph theory, that probably made sense, and for everyone else, it probably really didn't. Sorry. Does that make sense for people?
Are there any questions?
You just answered your own question.
Yeah.
Basically,
Yeah.
we're ensuring connectivity at the most minimum level without producing any loops.
Yeah.
But
Basically,
we do add loops later.
Right. The minimum spanning tree of a graph, a graph is a bunch of, nodes and a bunch of connections between those nodes. And the minimum spanning tree of a graph is basically you select the minimum number of edges so that every node in the graph is connected to every other node in the graph still, right? And so if we treat our connections like edges between our regions, which are our nodes, then if we can use some standard algorithm for computing the minimum spanning tree of that graph, we now know which connections we need to make junctions out of to connect our graph together, connect all of our regions together. And we don't actually implement that algorithm because this isn't a graph theory stream. We pulled in a library for that called Graph. And so really all of our code here is about generating the data structure that this library uses that corresponds to the sort of logical structure of our map. So, this carved junctions here, the first thing it does is it makes a tree. So with graph is make tree, and then that does actually the entire minimum spanning tree computation. It makes the graph in the format that graph likes, the graph library likes, and then it calls the minimum spanning tree on that, and then we get our tree out. So make, we make the tree, then we get out the edges from that tree, right? A tree is a graph. It's strictly a subset of a graph. So we take that tree, the graph, and we get all the edges out of that, which are the minimum edges we need to fully connect all of our regions. And then for each of those edges in that list of edges, we pick one of the connectors that would correspond to that edge. So each connector is connecting two regions together, and so we have an edge which connects two regions together. And so we pick one of the connectors that matches that edge at random, and then we make a junction there. Then we, this is the bit that adds loops. We do a random Boolean there, which, randomly decides if we should also make a second junction connecting those two regions together, or at least try to. That's all that, so cycle factor there is, determines relatively the number of times that each pair of regions that have an edge in our minimum spanning tree also get an extra connection between them. And then we, when that's true, we make an extra junction. There are a number of other ways we could have implemented the cycle code, but this was just the simplest one. And it does the job reasonably well, although it doesn't quite create as beautiful cycles as some earlier versions of this library might have, but those versions of the library were harder to make that into an option for the user. So, but anyway, so, let's look at make tree so we can see how we're actually constructing that data structure that graph wants. Make tree calls make graph, and that's where we get down to this function called graph populate. So there's make graph there. We call graph populate. We make a graph, the graph, and we call populate on it. And that's just a way of filling that graph in with the data. The nodes in that graph, of course, correspond to the regions of our map. So we pull the table of regions out of our map, and we count the number of regions in there, and then we use iota to make a list of numbers, that correspond to each of those region numbers.
So it sort of doesn't matter. We could have used
Can I ask a quick question here? Because I don't remember if we discussed this yesterday, so just remind me if we did. But in the graph library, the graph data structure, when you make an instance, does it not take any init args that you could just, pass in? I'm just wondering if you need to.
I don't believe so, but I'm not sure. All of the examples I've seen have used populate.
Okay. I was just kind of curious about that, because that just looks odd.
Yeah, go to make instance, graph. Yeah, there we are. Yeah, no, it doesn't. It actually takes absolutely nothing.
Okay, thank you.
I want to see what the doc say for that.
It just looks odd, I'm sorry.
I agree, actually. I agree that it looks odd, but that's the way that they wrote it.
Yeah.
Okay, so... blah, 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 blah.
Yeah, no, they're using populate as well.
Okay.
Or just add edge and add a node.
Yeah, they're adding edges, and yeah, you have to just create an empty, structure, and then fill it yourself.
Yep.
All right.
So that's the way they did it.
That's the way they did it.
Anyway,
yeah.
So populate there, and then edges with values. Basically, that we pull out connectable edges there. It goes through the hash table that we had. Actually, if you could scroll up just a little bit, we would see connectable edges.
Where is that?
It's just a little further up.
Yeah. Connectable edges. Okay.
Yeah. Basically, that. So we have that table of connections, right? Which is where we were saving off all of those cells that were connectors. But the keys of that table actually, correspond to the actual connections that we have, right? Each key is a pair of regions for which we have one or more cells that connect those two regions together. And so if we go through the keys of that table, we now know the edges we need to make in our graph. And so connectable edges just goes through...
You keep talking.
Okay.
I don't like the weights on that. I'm just going to use what you said, the hash table keys.
Yeah. Did we expose hash table keys?
Yeah, I think we did last time.
I don't think we exposed hash table keys.
I'll do it later then.
Yeah. Basically, the way this is written, it is explicitly assigning each edge a weight of 1, but you don't actually have to assign the edges a weight. Edges with values, before we screw that up. The key arg there is edges -v values, yes. Thank you. But yeah, so connectable edges there. Basically, it's just getting all of the keys out of that table, to represent, the ones where we have a cell that connects those two regions together. And then you just cons that with a 1 because we need an A list. basically an A list that maps from, the edge, which is the list of, the two nodes that it's connecting, and the value corresponding to that edge. We push that onto the edges, and then we return the list of edges. So not too complicated. And so edge values just takes that list of connectable edges. So once we have our nodes and our edges, we make a graph. Then back down to make tree. We made our graph. Then we pick a random node in our graph. The important thing is that we pick the random node. The minimum spanning tree function in graph that we're calling there, graph/graph minimum spanning tree, it will actually, if you don't supply an initial node explicitly, it will actually randomly pick one for you. But when it does that, it uses the common Lisp random number generator, not ours. And that's a problem because we need this entire thing to be deterministic in the seed that we pick for our random number generator. That's the whole reason why we have our own random number generation, stuff in the first place. And so what we have to do is we have to use a slightly more verbose part of the API, which allows us to explicitly pass in the initial tree of our minimum spanning tree with the initial node that we want the tree to start from.
Yes.
And so
this whole form right here is optional.
Right. That's computing, that's creating the tree explicitly ahead of time. That minimum spanning tree is going to populate with all the nodes and all of the edges. But we're starting it off explicitly with a node of our choosing that we picked using our random number generator, which is our, nicely deterministic one, as opposed to the commonly built-in one, which we have no control over. And so that way, we start our initial graph, our initial tree, off with that node that we picked. And we run minimum spanning tree, and it does it for us, and it returns the graph that contains just the edges that are absolutely required in order to make sure that all the nodes are connected together. And that, that does the entire thing for us. That actually figures out the edges that we need in order to make the entire dungeon accessible. Right, because the whole point of this is we want to, avoid the chance that there be a room somewhere that you can't get to, right? And so, the whole idea is that you're adding it, aren't you?
Yes, I am.
Okay. Don't you want to just inherit from? Yeah.
Yeah. What was it called?
Hash table keys.
Right.
Yeah. Just make sure that you push that eventually. Yeah. So basically now instead of manually pulling out the keys and pairing them up with weights of 1, since we aren't using the weights at all anymore, we can just, use a utility function for pulling out all the keys of the hash table. And that way we don't need that utility function at all. Much simpler. Anyway, so, once we have our tree there, which contains our minimum edges, back down in our junction code, you're committing that now.
I will forget.
Yeah, fair enough. You're missing an A.
A new keyboard, I told you. I don't care right now, I'm just trying to get it done.
Okay, so back down at the bottom, right? So that gets us our tree, and so now we can pull the edges out of that tree, and loop through them, and then we can make junctions at random connectors that correspond to those edges, right? And so maybe make junction isn't too complicated either. Then we pull out a kernel for that cell that it's the plus shape, the orthogonal kernel centered over that cell. Then we use this adjacent junction function, which just checks to see if there's a junction that's next to the junction that we're trying to create, because we don't want two junctions right next to each other, because that would be
not jump to the right part.
You've modified that file.
Oh, right. No, I didn't. That's saved.
Did you recompile that file since you did that?
Okay.
Sometimes the jump to definition code breaks slightly if you modify stuff and don't recompile everything.
Folks, this is a Sly issue, not a problem with the code base. I'd like to point that out for the newcomers watching.
Yes, this is just our.
I'll reload it. Okay.
Yeah. Anyway, so adjacent junction P, it just checks to see if there's a junction or a door it tries to detect for a junction or a door. So simple enough. We checked. We make sure that there's no adjacent junction or door, and if there isn't, we carve one, and then generate junction feature. Basically, it randomly picks either being a junction or a door. It's actually right above the cursor.
It's simple.
Yeah, picks by random boolean based on our door rate. Basically, this is just determining a junction is just could be a doorway, could be just a passage, could just be a continuation of the corridor. Whereas some of them we want to explicitly mark as doors. And so we pick either door or junction and we carve that. We remove the connectors that are adjacent to this junction. That's to make absolutely certain that future code doesn't try and make a junction adjacent to this one.
You see that the closest a junction will ever be is one step away. It won't be ever directly right next to it.
Yeah, if you note the connectors that are immediately to one cell away, the connectors that would be one cell away from each of those junctions have been removed. There's no orange dots around them.
Yep.
Then basically we detect once again if the distinct regions were vertical or horizontal, and that's just a hint for anyone who uses our data structure so that they don't have to do extra checking themselves to see if a particular junction has different regions horizontally adjacent to it or vertically adjacent to it. So that's all maybe make junction does. And so that's actually all of junction carving, if that made sense to everybody.
You're on a roll.
Yeah.
No questions.
Well, that's probably more because this is too confusing and people aren't understanding me.
Either it's too confusing, or you explained it so well that they're like, I can't answer.
Yeah, this is possible. I'd say there's a chance of that anyway.
Wait. Is anybody?
But it's a chance.
What was that?
I said it's a very slim chance, but it's a chance.
Yeah.
Okay. Well, at least you guys aren't sleeping. You got some feedback.
This is true. If you have any questions, feel free to interrupt me.
Any
honestly.
general questions is feel free to open up. This is clearly a case study. This is a good design. I mean, a great example of of how to write a common Lisp project. So if you have general questions too as well, feel free to ask at this point.
Yep. Then the last step is basically removing corridors that only lead to dead ends. Removing bits of corridors that only lead to dead ends. And so if we uncomment that, regenerate our stage. Ooh. That's unfortunate. What's happening there?
Oh, it's that change that I just made. Less than nil.
Oh, yeah.
That's actually in the minimum spanning tree function.
Yeah, because the minimum spanning tree expects there to be weights, because it's expecting you to be doing a minimum spanning tree using weights. So yeah, you can't remove the weights there.
Weights are absolutely required.
Nice. Okay.
It needs weights.
It's because of the algorithm that they're using. Since they're using graph uses prims, right? Prims
Yeah,
requires
and
weights. So
it doesn't technically require weights. It could just assume unweighted and just use effectively
random
just
weights.
extras.
Right. It could do randomization, and then you do make some assumptions on what could be done there.
But anyway, so this is our final rendering here with the edges that only lead to dead ends removed. And that way we can we have a nice simple map. Removing the dead ends isn't too tricky. It's a little weird. It takes some working through, especially since we now have to explain how the process function works. Right. So we're seeing now the difference in using really windy corridors versus not terribly windy corridors.
This is the same seed, just with perfectly wild factor at 0.
Yeah.
If you remember this, because I can't keep both of them open at the same time, and I change it to 1.
Much more windy corridors.
You can see this winds all around. It's just more interesting. You can control that as a float from 0 to 1.
I guess this might be related to random factor, but I've always wondered, like, in some cases where if a region is connected to two different...
Oh, keep going. I'm sorry.
In that example, if a particular region is in between two different corridors, I would have expected a door to actually be between both corridors, but it doesn't look like.
Well, so the thing is,
but I think it's related
since the corridor carving algorithm is greedy,
yeah,
right? Any place you could put a door between two corridors is also a place where the corridor carving algorithm would have just continued on.
Right. That's why I said I think it might have been a function of the way the algorithm was is being executed.
You can really see the effect if we make a more sparse map, not as dense, and then we change it. This is with 0, and this is with 1.
Huh.
That's amazing.
Yep.
That's great.
That's a maze.
Same seed.
Okay.
Mm-hmm.
Same seed. I mean, the rooms are places. Everything else is the same. Just the corridors are a lot more windy.
Yep.
Clearly, this is great that if we can print it out using a PNG, you've effectively made a nice dungeon generator for the D&D folks.
This is true. The orange dots look nice, too. But anyway, so uncarving the...
we can check that out. That's the road dead ends, and that is in corridor still. Okay.
Yeah.
Oh no, we're jumping back to corridor.
Yes. We put that one in corridor for reasons. You just added that one, I think. I don't remember. But anyway, so...
This is the one where you greatly simplified.
Yes. Yeah, so this one is done with 3 functions, but it uses this fun function called process, whose logic is a little complicated. But basically what process does is, and if we can, look at that. Basically what process does at a very high level is it's got a bunch of items, and it's doing operations on each of those items, and each time it does an operation on one of those items, that item is allowed to produce a new item that it should do further processing on. And so the idea there is that the items are going to be our dead ends, and each time that we remove one of our dead ends, that's either going to one of our dead end cells in particular. It's going to be a bunch of cells that we've marked as dead ends, and each time we uncarve one of those dead ends, we're going to move that corridor back by a couple of cells, and now we're either going to have another dead end, or we are going to we'll have carved back to like a branching point in the corridors, and that cell's not a dead end anymore. There are other places to go from there. And so basically the idea is that if we uncarve that cell and we find that we still have a dead end, we need to return that new cell there so that process uncarves that one too. And so that's all process is doing. It's got this list of things it needs to operate on, and each time it operates on one of them, that thing is allowed to return a new thing that process has to operate on. So with items, it's just our list of items that it's operating on. While there are still items, we call this generator function on the first thing in the items list. We pop that thing off the items list, and that produces a kernel, although the code here is actually generic enough that doesn't have to be a kernel, but that's how we're using it, and so we just named that kernel. We call this filtering function on that kernel, which decides if it's something that we still need to do processing on at all. And then we call our processor function on that kernel, which it does the processing on that kernel, and it is allowed to return a new thing that needs to be pushed onto items and handled in the future. And so that's how we're using process here. We pass it a stage. We don't supply a layout because the layout is actually only needed at that level if we want process to figure out the items to operate on its own. But we're not using
functions were written way too generically.
Yes, yeah. Process is a lot more generic than we needed, basically. So we don't need the layout argument there. And we don't actually even need pretty much any of that first line there, the with items equals or items collect stage layout filter, because we just pass in the items ourselves, which if you see over where we call it is the dead ends that we recorded earlier when we were carving out the corridors. So we start the items list out with the known dead ends, and our generator function, which is the thing which operates on each item, basically just it constructs a kernel centered on that item. The kernel centered on that dead end, basically, because each of the items will be a dead end. We call our filter dead end function, which makes sure that that the thing that you're operating on really is a dead end. This is just to make our life a little simpler. We probably don't even necessarily need that filter, but it's good just for sanity's sake. So we have this filter dead end, and it basically it looks at all of the.
You're saying it would work without the filter dead end?
I don't know for certain. I suspect we don't need it because we're being careful about when we return another cell to process. I'm pretty sure we only will ever have.
I want to try. Constantly G.
Yeah. Watch, it's going to completely break and I'll be completely wrong.
It breaks.
Yeah, it completely breaks. Completely wrong. Ignore me.
What happens if we never do it? Probably just the end of last step, yeah.
Right. Anyway.
That's crazy.
So anyway, we aren't being as careful as I thought we were. Oh well. So basically, filter dead end there, it takes that kernel, right, which is centered over the cell that we've called a dead end, and we map carved P over that, which basically gives us a list of the of booleans, right, for each one, whether or not each of those cells is carved, and that includes the cell that we're actually on, cell 00.
I'm stepping away for a minute. Just keep
okay.
going.
And so we count the number of nils in that list, and so those are the cells that aren't carved. Basically the idea is that as long as if there are at least 3 adjacent cells that aren't carved, we know that we've hit a dead end, right? And so really the test is, well, is the cell that we're on carved, and are all of the cells that are adjacent to us not carved, or there are at least 3 cells adjacent to us that aren't carved, because that means there could only be 1 cell adjacent to us that is carved, and that's the cell that we're backtracking out to. And so filter dead end just makes sure that the cell we're on is actually a dead end. Then we call this a row to dead end function, which takes that same kernel. It uncarves that cell at position 00, and we'll look at that in a minute. Uncarve just it undoes all the work required to carve that cell. We remove the connectors on that cell and adjacent to that cell. Just it gets rid of all of them. We remove all of those connectors, and then we run that our fun little kernel detect function there. Basically, that this is for determining if there's another dead end adjacent to us. Right. Basically, we go through all the adjacent cells, and if any of them are still carved, we return the first carved one we find. Because we've since this is a dead end, we know that the only carved cell that there could still be adjacent to us must be the next dead end in or next potential dead end in our corridors, right? And so that way it returns that cell as the next cell that needs to be operated on, right? So that way basically we sort of backtrack out from the dead ends we have back in until we no longer have any dead ends. So does that make sense to everyone? It's a little complicated, I suppose. But it goes through and it removes one of the dead ends, and then that reveals another dead end, and so it removes that one too, and it reveals another dead end, so it removes that one too, and it keeps doing that until there aren't any dead ends left.
So let me just look at something, because this one I didn't see this yesterday, but I do have a question on this actually.
Yeah.
Which
sure.
is so the definition of dead end is that they're not essentially
There's
connected
at most
to
one
A
adjacent
dead end
carved
is
cell.
a cell with three walls on three sides.
Three
There's
walls
only
on three
one
sides.
way. There's only one way to go. It's backwards.
Okay, gotcha. That's what I wanted to make sure. So basically, you're guaranteeing that if there's no connection, there's no path to either another region or whatever. It's completely surrounded. Then you are considering
right.
that.
Orthogonally, yes.
Yeah.
Well,
Okay.
actually, we always draw walls around it, so there wouldn't ever be diagonals anyway. So yeah.
Probably not.
Okay.
Though we've seen odd edge cases involving diagonals before, so I don't
We
like
fixed
assuming.
that.
Yeah, we did. But anyway,
that makes sense.
That's
makes
the
sense.
entire thing.
That's really cool.
If we look at this, okay, this is our stage without the last step of eroding the dead ends. What it's going to do is it's going to convolve over the whole stage.
No, it doesn't. It doesn't need to, because remember we collected all the dead ends before.
Yes, when we carved our junction, when we carved the corridors, we kept track of all the dead ends. So
Yes.
this cell right here is going to be in a hash table somewhere.
Right. That's what I figured. Okay, and the one below it also, right? Because
No.
But when this is removed,
it will be exposed, and that too will also be removed, right?
yeah.
Right.
Okay.
Yeah. So erode dead end, right? It'll get that cell there, right? It'll uncarve it. It'll remove any connectors that are adjacent to that. Like the one to the left of it.
And then it will expose the fact that the one below it is also technically, by definition,
right.
a
Yeah.
dead
See,
end.
so that kernel detect there, right?
Okay.
It's going to look at all those 4 adjacent cells, and it's going to see that one of them is carved, and it'll return that one.
Gotcha. Okay. All right. That makes
And then because of the way process works, when the processing function returns something non-nil, it knows that that's something further that it needs to do processing on.
Gotcha.
And if you look at the screen, when I regenerate it at that specific area we were talking about, you can see that it changes.
Yep.
It removed those 2 cells there, and all the other cells.
Just a small
leaves the
tangent.
path to
Why
the
is it
room.
that you ended up drawing 2 windows there?
Just a bug in Sketch. My
okay.
implementation of using Sketch.
Gotcha.
Yes.
It's just a bug.
Okay.
I only put a little effort into my renderer, whereas Elijah spent a good 2 weekends on it.
Yeah.
On his McClim renderer.
Yeah. When it works for people, it's nice, but
Mine literally took about 20 minutes to write.
yeah. Whereas mine is significantly more complicated. And actually, I think I can simplify it a lot further, and I'm tempted to spend a little time simplifying it. But for the most part, it's done now. I don't think that I need my off-screen rendering trick. I think I'm going to test that.
Okay, well, consider
But anyway.
7 o'clock.
Yes.
I do have to step away. I will still be on the stream. I just won't be talking. I'm going to leave this time for Elijah to show off his work on his renderer.
Yeah.
Okay.
All right. So give me a second here, Elijah. I'm going to go ahead and switch over to you if you can show your desktop.
Yeah, give me just a second.
All right.
Actually, Michael, could you stop sharing?
Yep, I will. Oh, it's down here.
Cool. So everyone good?
Yep.
Let's make sure that I actually have something workable. And I know you can't see in 1 second. There. That's better for everyone?
Yes.
Okay, 1 second. Yeah, that'll be fine.
I think you may want to mention this one thing to folks, which is those of you who are downloading this code and want to try Elijah's McClim renderer, I think it should be noted that right now,
McClim is broken on the most recent version of SBCL.
Yeah.
From my testing, at least, I'm pretty sure that's what it is. Because I can reproduce a memory fault when I launch it using SBCL 1.4.10 that doesn't show up in the version that I use most regularly, which is SBCL 1.4.8. So I'm going to be showing this using SBCL 1.4.8 because it works in SBCL 1.4.8, and hopefully the McClim keep will fix that soon.
Just a heads up for you folks who downloaded the latest version of SBCL.
Right.
It
won't work because McClim itself is broken on that version.
Yep.
And just as a reminder, everybody can find our code on the AFP GitHub that Ram will link to. I don't have the link on hand right now.
Yeah, I'll post a link on the basic info inside the YouTube channel. In the YouTube video once we're done here.
Okay, I'm stepping away. Have a good night, guys.
Night.
Thanks.
So my McClim renderer is I really like it. It does the job. Takes a second to load, but once it has loaded, it looks rather nice. It bothers me that
you really did work through this, didn't you?
Yeah, I may have put a bit too much work into it, to be honest.
You're almost at a full level editor, sort of like kind of like design.
Almost.
But yeah, I think it's really good.
It's really good.
So the way that it works right now is all of the sliders actually update the map live. The text boxes do not, because there's just no really good way to make that work and not have it feel really laggy when you're typing. So when you modify one of the values here, 65, you'll notice this Apply New Settings button grays out if I don't enter in a legal value, like if I enter in an even width, because this thing requires odd widths, and then you can hit Apply and it'll re-render it.
Can I ask you a question? So
yes.
This is a Klim question.
Yes.
Can that button be added into like some sort of like spacer to make it look like a proper size button, or is there no spacers?
Plenty of ways. I just didn't want to put the effort into that because I don't really know what the most aesthetically pleasing way of positioning that button is.
No, that's fine. I was just kind of curious because it was like it's a big button, right? So
yes, it is a really big button. Yes, I agree. And I don't really like that it's such a big button, but I'm not entirely certain what else I would put there.
Well, is there? That's why I was asking. Like, I know in like Qt and like Qlot, I think. You have like
I can
V spacers
1 second.
or
Let
whatever.
me just add a fill marker.
Oh, that's what it's called, a fill marker?
Yes.
Okay.
Well, I call it a fill marker. It's the constant fill.
Okay.
You just stick it in something and it fills in as much space as it can.
Oh, wow. Okay. That looks better, but it's not.
Here, let me transpose that, now the button's there.
Yeah. That looks better. It actually looks a lot better. So
the default cell size in our files right now is 29, because that was what made it look nice on Michael's 4K screen. Whereas for me, like I max out at like 20. At that point, it becomes a little ridiculous. And so when the thing starts up right now, you don't actually see the slider's little knob because it's over here somewhere. But if you just click somewhere, it'll figure it out.
What is the checkbox there for?
Whether or not we're drawing the connectors.
Oh, okay, gotcha.
Hence why it's labeled draw connectors. I don't know if you guys can read any of the text because there's no really good way for me to scale that, unfortunately. I might be able to, actually. Maybe. I've never actually worked with McClim text styles, but I could probably set a default text style on the entire frame that has the font a lot bigger.
Really, the draw connectors label should be in a panel horizontally next to.
Yeah, you'd think that. I can't quite get that to look nice.
Okay, gotcha. That's something to explore. Like I said, these are more general Klim questions.
Let me try something else. So let's see.
Didn't mean to get you straight like into McClim.
No. Horizontally, and then if I Klim vertically, and then I add a Klim fill.
Yeah.
There. Yes. Let's see what that looks like. How about that?
Oh, that's much better. Oh man, that looks no, because now it's clear, right? You could tell what the checkbox is next to.
Actually, I think I'm going to change that even. I'm going to transpose those.
Yeah.
I prefer having the checkbox on the left.
That's standard usability style, right? Always have the checkbox on the left, not the right. Most people will get frustrated with that. Yeah. Cool.
There we are. Ta-da! So this is what it looks like. It will resize to fit whatever space you give it. It needs, some minimum space, of course, but it will resize to sort of fill whatever space it needs. And
And you
And
said you said that if you move the sliders, it will update in real time.
It'll update as soon as you lift your mouse up.
Okay, gotcha.
Because the trouble is the rendering function in this is a bit slow to actually have it happen in real time. But you know, you only have to hit the Apply New Settings button when you change one of these text box settings. You know, 201.
And
Yeah, when you get.
Ooh, nice.
Yeah.
Just stop by again to check it out. It looks real nice.
Thanks.
It's really, really nice. I mean...
Oh, you know what you should do is you should make the stage less dense and show the meander rate. In real time almost.
Room density much lower. And so when we take this really low, looks like that. When we take it really high, looks like that.
Really nice.
Here, let me decrease the size of this again so that like we can actually, like if I take this down to like 33 by 33, it renders in almost real time. And so if we keep the room density pretty low, we can like really see how much more meandery it gets.
Wow.
As you increase that. Gets all nice and you know, wiggly.
That is impressive. That's impressive right there.
Yep.
Just one question though. Did you I don't know, is this doing the off-screen rendering that you mentioned that you were
it is. I suspect that it doesn't actually need to though.
Okay.
Because and actually I'm really tempted, and I may just go ahead and do that right now. Get rid of all of the, you know, code that I wrote to render off screen, because I don't think it's actually necessary. Because McClim is actually pretty clever about making sure that it doesn't redraw stuff when it doesn't need to.
Mm-hmm.
It's just I'm not certain what the performance difference would be, and so I just haven't really tested it yet. I could do that now, or I could tinker with that later. It depends on what you guys are interested in seeing. Well, I could show you guys a little bit more of how this code works, though.
One question is based on our discussion of the output recording, right, that I had. Right?
Yes.
The output recording is just a visual tree of the changes of a particular, I guess, widget.
Yeah, the output recording is a tree that describes all of the rendering operations that happen on screen.
Okay, and so if a change happens and it needs to percolate across to some sibling widgets, I guess it's the output recording that has to handle that?
No, actually. I'm not really doing anything with the output recording here at all.
Oh, okay.
This is much simpler and actually much more familiar probably to what you're used to in a UI library, okay, if I show you the code here. The only place where output recording would come into play is with this place here where I'm actually drawing stuff using the proper rendering API.
Okay.
The widgets, while these are implemented as the CLIM built-in widgets because the CLX backend doesn't have any native widgets to use, while these do technically use the same drawing operations internally, that's entirely abstracted away. The widget API doesn't expose the drawing functions pretty much at all, specifically so that backends have the ability to use native widgets that, you know, may not correspond to anything involving how output recording or any of that stuff works.
Okay.
The output recording is purely for the rendering API.
Okay. Thank you.
Yeah. So, you know, this code here, I need to make that just a little smaller for me. Yeah. Can you guys still read that?
I can.
Okay. I can make it a little bigger. How about that?
Yeah, that's fine for me.
Okay, good. So the first thing that we have here is like everything like there, yeah, all of that stuff, a lot of stuff, I suppose. Everything up to here, everything before CLIM define application frame, is part of the custom code that I wrote so that I could completely take control over how the rendering of the stage works. So basically, there's CLIM works using these ideas of frames, sheets, and panes, and gadgets, right? So we sort of have these four abstractions. A frame is the entire window, although it doesn't necessarily have to be a literal window on the back end. It just represents sort of logically, it's some interactive part of the UI that has its own event loop and has its own interactions with the user that are independent of other things on screen. And so generally, it's represented as a distinct graphical window on screen. And so each frame is usually a separate window. And so the frame is broken up into panes. And so actually this right here is a pane, this whole thing here. Actually, this is a whole bunch of little panes down here. Like the slider itself is a pane, and this little label here is a pane, and this label here is a pane, and that label there, and that, this gadget and that label, and these labels and these gadgets, and each of these things is a separate pane, basically. They're sort of logical sections of the UI. And a pane can be implemented basically by anything the McClim backend wants it to be, and can lay it out on screen. And so this is the, panes are where the backend can do clever stuff, basically, to make it look native, for example. And so, then we have things like these sliders, which they are panes, but they're a particular kind of pane called a gadget. One that's designed to sort of be self-contained, and some logical bit of interactive UI is a gadget.
So text fields are also gadgets then?
Yes,
okay.
The text fields are also gadgets, and this checkbox is also a gadget.
Okay.
So that's how that terminology works. Every gadget is a pane. Not all panes are gadgets. So then some panes are what are called sheets. Well, sheets are kind of a distinct part of Clim, but the general way that you get a sheet is that you use a pane that provides a sheet abstraction to you. So what is a sheet?
Okay, you're getting really into Clim here. This is...
Yes. I want my code to be understandable, at least to some degree.
All right.
I'm only going to go another couple minutes here.
All right.
Don't worry. A sheet is something you can draw on, basically. Some place where you can have much more complete control over the visible aspect of the screen. And actually, sheets are really flexible because you can invoke really complicated bits of McClim's rendering API with them. You can also actually use a sheet as a text stream, so you can actually do things like you can print on a sheet, and it will it'll take that text and it'll format it on a particular spot on the sheet so you can see it. Sheets are sort of the part of Clim's very flexible sort of API for making interactive graphical applications that use custom graphics. And actually, sheets can be nested, and so what's actually going on here is this entire thing, since I'm using a backend that doesn't actually provide custom implementations for any of these gadgets here, this whole thing is actually a sheet. And each of these gadgets here is implemented using a Clim implementation that just relies on the sheet rendering API. And so these are using Clim's internal drawing functions atop a sheet. But the only place where I can actually see that it's a sheet is this pane here, which is an application pane, or one that is absolutely guaranteed to be implemented using a sheet, and where I can control the rendering on it. And actually, this isn't technically an application pane per se, because it's actually a custom pane that I've implemented, but it's the same basic effect. It's that I know that this particular pane has a sheet associated with it, so that I know that I can draw directly on it. And so I implemented this custom pane here, which allows me to very carefully control how drawing happens. And the important bit really is this function right here, draw stage. This handles the entire drawing logic of the entire stage in that area. I draw a rectangle there, which is the size of the entire visible region. And, or actually, truly, it's the size of the stage, the entire, the stage that we're drawing. And that's just to blank out the background. I make that the wall color. And that way I can avoid having to draw actual cells for the walls. I could just leave them blank. And then I basically just go through each cell in the width and height of the stage, and I check if that, it's not a wall, unless it's a wall. I draw a rectangle there of the, proper size, and I get the color from the select color function that we implemented sort of generically so that all of our backends could have the same colors. That returns just an RGB list, which I pass to this make RGB color function. We were actually seeing that select color function earlier. That's what we were editing in order to change the color of the doors. I don't have those changes because that hasn't been pushed and I haven't pulled it yet, so that's why the doors look blue for me still. And I could change that if we really want, but I'm explaining McClim stuff now. So then down here, it's just, I have this, if we're drawing the connectors, and the thing was a connector.
We have a question in the chat. Someone asked why the nested loop, though. Couldn't you just more easily?
I could have made a single loop, but then I would have had to compute the x and y positions by hand in other ways, right? I still need to know the x and y position on screen, right? I could have done a single loop through all of the cells and extracted the x and y of that cell. Like, I could have gone through the stage, and I could have extracted the array inside the stage, which is a 1D array of cell objects, and gone through each of those cells and extracted the coordinates stored. I think the cells know their coordinates. I'm pretty sure. Yeah, they have to. And just extracted that and used that. But that's not how I implemented it. I went for a nested loop, just because I felt that was simpler for my brain to understand at the time. And it doesn't really make much of a difference. Either way, it's just I draw rectangles when there needs to be a rectangle, and I draw a circle anytime it's a connector. And I use that same select color function, but this time I pass in circle instead of rect, which gets me the colors for circle-shaped things. And that's really the important function there. The rest of this is this function here basically uses that draw stage function and draws it to an off-screen, an off-screen image. And then this handle repaint function is actually a McClim function that actually does the copying from my off-screen image to the screen here. And, it's not terribly interesting. It's just McClim internals. Well, not really internals. This is public API, but it's pane implementation stuff. And generally speaking, you don't really need to do that unless you have, some particular need to take very low-level control over how drawing happens. I could much more easily have written a much simpler function that basically was literally just this bit here. It's just, it could be a little slower, and there are some interactivity things, and I don't know when this gets called and how much it redraws the entire thing when it gets called, etc., etc., etc. I'm actually going to be testing later exactly how much slower it is if I just use this function directly and don't draw off screen and just draw directly to the screen and such. But then basically the main thing is this application frame here. That's what defines the renderer. And basically I define each of my panes. I don't define all of the panes there. I just define the ones that I need to have names for. And so those are the sliders, the text boxes, the buttons, the check boxes, those panes, and this pane here, my custom one that draws the map. Top level here is that pane, the one that draws the map. It's my stage display pane. And I set the cell size and the connectors, and that we're drawing connectors. And then basically here I make a text editor, and basically Clim has this sort of shorthand for if you're making one of the sort of built-in panes, which you don't have to say explicitly, this make pane bit. Really, this is just shorthand for if I did Clim make pane like that. It's just, wrap it in an extra pair of parens and start with make pane. But since it's one of the built-in ones, I don't have to do that. I can just say text editor there and just give the key value pairs that would go into making the pane. And so this is just, the width, it starts out with, I get the attributes out of our stage, or our frame. Our frame stores the p list of attributes that we use to instantiate the stage. I get out of that the width, and I default to 49 if the user didn't supply one when they created the renderer. And then I make that a string, and then I set that as the value, the starting value of our text editor. And I do that for each of these, the text editor ones. That's each of these. That's why these, when you don't say anything, they start out as 49, 49, 1, and 11. But I could pass something when I call the render function and start the renderer. Here we have all of the sliders. These are a little more complicated because I have to specify much more complicated, bounds checking and, whether or not we want to have a preview of the current value and how many decimal places and stuff like that. But otherwise it's pretty simple. It's just, min value, orientation, show what it is. Then we have our apply button, which is, this thingy. This activate callback is the function that gets called when you hit the button, and it calls this render map for matters function, which just, it takes the current attributes value and it renders the map based on that. Did I just change something? Then we have our draw connectors checkbox and our cell width slider, which are these two down here. And with these, I specified a value changed callback, which is a function that gets called anytime you, change the value. These also do have something happening on their value change callback, but I actually handle them all in bulk in a function we're going to see in just a moment.
So I have a general question.
Go ahead.
So in that activate callback, I noticed that this was a lot in Michael's code too as well. But what is the effect of that declare ignore exactly? Like what
it makes sure that SBCL doesn't yell at you for having a variable you're not using.
Oh, okay.
And it also, if you do use that variable later, it forces you to notice that you've used a variable that you previously said you were ignoring.
Okay.
There's also another one called ignorable, which just suppresses the warning but allows the user to use it if they do decide to. And that's good when you have a variable that's generated by a macro and you don't know for certain if something else is going to use it and you want to just blanket suppress any possible warnings that could come from that variable.
Okay.
I don't think this has been talked about before, but the Common Lisp standard, 99% of the declare forms are they don't have to be honored by an implementation. There's only two that do, and that is declare special for special variables and declare not inline.
Yeah.
Those are the only two required to even be seen by a compiler.
Yeah. All the other ones it could just completely ignore. Ignore. It could ignore the ignore declaration.
It very well could.
Yeah, but I mean, ignore it's really just about suppressing potential warnings the compiler might give you.
So these are just hints to the compiler to say, by the way, I am purposefully doing this.
I know that I'm not using that variable. Yeah. You don't need to tell me.
You don't need to tell me. Okay, gotcha.
Yeah,
all right, I'm with you now.
Yeah, and so that's all that is.
Okay.
It's just McClim passes you the actual button object, and I don't need that button object because I'm just calling some function. So I call this value. I set the value change to callback for this, the slider for the cell width, the draw connectors, and I set that specially because these don't affect any of the validation logic, and I have a single bulk function later, and they also don't affect the attributes of the stage. These don't change how these don't actually affect the actual stage itself. They just change how big it is basically and what we're drawing. And so I gave custom value change callback for these because I wanted those to be separate functions. Then we have the layouts here, which and I define a single layout, my default layout, which basically just it's the way everything's arranged on screen, and you can basically this is just a pane. A layout is just a pane, but generally you use the panes that are called composite panes, things like horizontally and vertically, which combine a bunch of other panes together and lay them out in a particular way. And so horizontally, I say these two panes here are laid out horizontally, and they each get half the space. So that's what gives my vertical split here. And then vertically, we inside of a scrolling pane, that's what gets me my scroll bars. We have my top level pane here, which is the one that's drawing the map, and then horizontally, we have these two things, and then vertically we have some labels, and so you can see how this constructs this whole structure here. It's basically just a tree. Tabling is the only really complicated one there, and that's the reason why all of these line up nicely. Basically, I can give lists of panes, and each of these lists forms one row in a table. And each subsequent item, the first item in each of these lists is going to have the same width, and the second item is going to have the same width, and that's why everything lines up in nice columns. With the stage seed, I had to do something a little more clever because I only get, 2 columns here. And so that one is sort of snuck in there, and I did that by just, making another horizontally. And so this is size to that second column, and, we horizontally have both our stage seed, widget here, this one, and we also have this extra little button which just makes a new seed, and all it does is it sets the seed in that, seed in there. And actually, that should probably be T. It doesn't matter either way in this particular case, but I think in that case it should be T. All this does is when I set the value of a gadget, that's saying whether or not to call the value changed callback and invoke, all the other logic involved in what happens when you change the value of something. And so this is basically like if changing one value, affects other values, we may not want to recursively invoke value changing logic, as this is a way that you can break that recursion. And then I just make a new seed. Make seed is just a function that's in our library. It's the function that's used internally for making seeds. And I just make a string out of that, so that is the value. We have our apply button, and then we have that fill marker, which just makes that this takes as much space as it can. That's basically the entire layout. That's the entire application frame. And then we just have the extra logic down here, render map from attributes, which takes the attributes out of the frame, and it makes a stage out of them by just, applying that plist to make stage. And then we get out my top level pane. We call this function clim find pane named, which you're going to see a lot of in a moment, which takes our frame and the name of one of the panes, one of the named panes in particular, one of these, and gets me back that pane. And then I basically set the new stage that we just created as the stage field on my top level pane, and I tell it, hey, redraw that stage, since you now have a new stage. I don't think I do use this. Then this right here, this function here, the value changed callback, right? Remember I said that I defined a custom value changed callback for 2 of these 2 here. But for all the other ones, there's this generic function called, clim value changed callback that I use. And this one's nice because it gets invoked not just on the gadget, but actually also on the frame. Basically, each gadget has this concept of what's called its client, the thing that is using the gadget. And when the value changed callback runs, it calls this, or when the value gets changed, really, it calls this function with itself and its client and the ID of that gadget and some new value. And that way you can define methods on this to do all the value change logic instead of defining individual functions. Basically, the default primary method on value change callback is what actually calls whatever function you specified right here. Is the value change callback function. Is done by the default method of this. This is a whole lot of logic. But basically all it is me recreating all of the validation logic in the options file. We have this verify options function here, which goes through all the options and makes sure that they're all okay. I basically do that same basic thing. I don't have to do quite as much because all of my, all the slider ones, density, door rate, cycle factor, all of these, I don't have to do any validation on because just the way the UI works is going to keep those as valid values. But for like seed here, I have to, I find pane name, stage seed. I get out the value of that gadget. I try to parse it as an integer, which is this function I've written up here, which parses an integer allowing junk, and it returns, it defaults to 0 if there was junk instead of, in all cases, if there was no integer to read, right? Because parse integer, it'll return as much integer as it can, right? It goes forward and it goes and it keeps parsing off digits until it finds something that isn't a digit and then says, okay, that was your number. And then as the second return value, it tells you how many digits it parsed off. And so that's a way, if you have a string that contains a bunch of text and it starts with a digit, you can pull that starting digit off by passing junk aloud. But in this case, I'm using that so that if the user passes something that isn't a number, or isn't entirely a number, I know. Basically, I make the second return value be, well, did it parse the entire string, right?
That parse integer call there is only going to return nil
if there was no digits. Yeah, I know.
No, not entirely. That's not correct.
Yeah. Here, I tested this.
I will show you a test.
I will test it right now. Parse integer 5 foo junk allowed p, right?
Yep.
And in this case, it returns nil. And in that case, it returns nil.
Okay. There's still a test you haven't done yet.
Oh, when it starts with something that isn't a digit? Right.
Try foo 5.
Right, exactly. I know. It only
So
looks
that still contains a digit, and it's still returning nil. That was my point.
Yeah, but I don't care about that case.
I'm just mentioning it to our viewers that parsing
Yes,
will
fair
return
enough.
nil if there is preceding junk. It only returns a digit if there's junk after the digits.
It's a suffix.
What happened to you being gone, by the way?
I'm idly nearby.
Fair enough.
Jump on.
It's a suffix
yeah,
cut
so
rather than a prefix, right? So it's not. It's not trimming off the solid. If there's a mixture, I'm assuming also that it will only grab the first integer that it finds. So if you have like 5 foo 5, it's only going to get 5, not 55.
Right. 5 foo 5. Yes, it'll only get 5.
Right. So it's essentially trimming off the first until once it hits the first integer, right?
Yeah. So it basically just it expects there to be. I think you can have white space at the beginning. Yeah. So you can have white space at the beginning, but otherwise it has to start with digits, right? And it will keep parsing until it hits something that isn't a digit, and it'll return the number that it came up with, and then it'll return how many characters it got in. It'll return the index of the first non-digit character.
Got it.
And so in my case, I just want to know if it parsed the whole thing as a number, and if it did, I'm good, and if it didn't, the user didn't give me a number, right? Now, if the user enters in nothing, that will also parse. It'll return 0 here, and this will return true. And so that's technically valid if you don't supply anything that comes as 0. However, a 0 width, or like for most of these, 0 isn't a valid value anyway, and so that just doesn't pass any of my validation logic.
Interestingly, I just tried \space a digit, and that works.
Yeah, no, that makes sense. Right? Because \space is just space, right? Because it escapes the space.
Oh, right. Okay, I wasn't thinking about that.
But anyway, so here is all of my validation logic, which is so fun. It's all of the fun. But this is really all of this is just coming up with values before I can do the validation. And then here's really the validation call right here. It's if we parse the full width and it was odd, if we parse the full height and it was odd, if we parse the full seed, and if we parse the full room extent. And then I have this here, which is it basically just makes that plist back together again. And then this last bit here is, when seed wasn't 0, basically, actually that means, of course, that you could supply 0 as the seed, and that would give trouble. I should probably fix that.
No, because that would fail in the stage, because I believe a seed... I believe a seed is specified to be a positive integer.
Ah, okay. So if you supply 0 as the seed, it just generates a random seed every time. But you don't know what that seed is, because it's internally generating a seed. So don't do that. But basically, either if you don't specify a seed or you make the seed 0, it's going to do that. Also, I just realized this code probably breaks if the numbers are negative. No, it's good.
Does it still break if they're really small? Like 5 instead of 45?
Yeah, that breaks. Or no, it doesn't break, yeah. Because the room extent isn't valid in the case where the width is 5.
Okay. What if the room extent... Oh, okay.
You can't pick a room extent that's small enough to satisfy that.
Okay.
But yeah. So, basically, this function here, it has this, the new attributes and whether it's valid. If it is valid, we activate the apply button. That's what, is what's graying this out, is when we had valid stuff, it activates the apply button. It sets the attributes. And then this here, when the gadget was a slider gadget, we render the map. And otherwise, we if it wasn't valid, we deactivate the apply button. So that's the entire logic there. And then these are the callbacks for the two sliders, the slider and the checkbox at the bottom is new cell size. It just sets the cell size on my custom pane, and it redraws. And in new draw connector setting, same thing there. I don't think I need this function here. I don't. Get rid of that. I don't know if I need this function. I do use that one somewhere. Oh, yeah, there. Yeah. Right. So this basically, that's really all there is to it. The rest of this is just, minor stuff. I should probably move that higher. This is my shorthand clim label, which makes a label pane with some text, because I got tired of writing clim make pane label text.
I got tired of looking at label, both keywords next to each other. It was kind of confusing.
Yeah, that's why
the keyword like that.
Well, I mean, they're all named with keywords. All the built-in panes are named with keywords.
Oh, that's kind of odd.
Oh, I mean, those are abstract panes. The idea they aren't any particular pane. If you pass a symbol there, a non-keyword symbol, you're referring to a particular class, an explicit instantiation of a pane. Whereas if you use a keyword, you're leaving it open to the back end to pick which pane to actually use for that.
Oh, okay.
Yeah. So the keyword ones are abstract in the sense that the back end gets to pick which concrete class to actually use to implement that.
Gotcha.
Yep. And then this one here is my method on the render function, and it basically does a pretty standard, clim process. This right here obtains a frame manager, or obtains a port, which is really getting the port is the core of opening up connection with the backend. Then a frame manager is just something that I can tell to host my frames. And this is basically just the combination of these two abstractions is just part of how Clim's frame management works. But then I make my frame. My Clim MacGen renderer. I call make application frame, which is a wrapper around make instance that also does a couple Clim specific things. I pass into my frame manager and the attributes that get passed into the render call. Get my frame, and then we have this bit here, which is add this run function, which makes my frame, and it does some stuff, and in an unwind protect, and when we exit, we disown the frame from the frame manager. This basically removes that window from the screen whenever this thread dies. Basically, this is the logic that makes sure that no matter what, no matter how we exit on this, be it a clean exit or an awkward one, by some error, we make sure that we clean that window up. That's what that's doing. And then this right here is just making sure that I don't accidentally leave an off-screen buffer allocated, because it wouldn't be particularly good if I just allocated a bunch of those and left them around. But then I use this function here, clim_sys_make_process, which is basically it's spawning a thread. I can use Bordeaux threads there. I can use bt make thread. It's basically the same thing. And both are just wrappers around an implementation specific function for making a thread. And then just for my own sake, I haven't returned the frame there. And actually, probably the best thing to do there would be values. There, so I get both, because having a reference to the process is useful as well. But anyway, that's the entire thing. That's the whole renderer.
Cool.
So that's in the Clim application. It's like in 20 minutes, just going really quickly through one. A lot of McClim stuff there, but hope you guys got something out of that. I suppose we can always do a much more in-depth McClim session if we ever decide that's a good idea. I don't know if it's a good idea right now, given how unstable McClim is, but clearly you can use it for things. Oh yeah. See, when this is gray, all of these.
I mean, if you're interested in McClim, clone our repository and play around with Elijah's renderer. You might learn something. It's pretty nice to play around with. I was learning stuff. I think this is valuable as a good educational value. This code base that we made over the past 3 weeks.
And this is a good introduction to Clim. We will have a more thorough introduction. I would feel that it definitely requires a more thorough introduction to the Clim library, which it's in the planning stages. I don't know when we'll get to it just yet.
Yeah, it may have to wait until we know that we can have Clim work for everybody. Because right now Clim is buggy on SBCL, and it only really has an X backend, so it only really works on Linux. Although there's some work to make an SDL backend. Yeah,
nasty bug that I encountered reproducibly.
Right, yeah. You mean your unhandled
Not
right.
The memory fault. The one where it takes out X completely with an NVIDIA driver bug.
Right. Yeah, that's terrifying. I have no clue how you manage that. And I have no clue how to debug it either.
Yeah.
But one thing at a time, I suppose. Part of me. Well, it's not that. It's that we can't get any debug info from Clim if it crashes the X server. I suppose you could run us BCL on a separate TTY and pass the display manually so that you know that you're not crashing the X server where you host your editor that's running SBCL, and that way you'd be able to debug it afterwards. Maybe if things aren't totally trashed, but yeah, that's weird. But one thing at a time. We need to figure out, or someone, probably one of the Clim devs, needs to figure out what the heck that unhandled memory fault is when you run SBCL when you're in the latest SBCL. Because at a minimum, that's all kinds of nonsense. And I can also reproduce that it breaks the listener pretty much in the same way. So McClim needs work. They are also working on a new theme for it that'll make it look a lot nicer. For those of you that hate the look and feel of it right now, McClim has a system in it for completely abstracting away the look and feel on screen of the widgets, as I've sort of been hinting at or mentioning explicitly repeatedly. And they are working on a theming system, and they are working on a theme sort of based on material design, which is Google's sort of style guide for UI. So it's making progress. I mean, Clim is funded, and it has a lot of active development work on it, and it's got a lot of little bugs, but it's making progress. UI libraries are tough, but it'll get there.
Again, I think we should definitely this is the start of I would say an eventual detailed talk on how to write Clim applications. But certainly you have I think an example to play around with. If you have a working if you work with SBCL 1.4.8 or earlier.
Yeah. But all I'm guaranteeing right now is it works on 1.4.8. That's the only one I've tested on.
All right.
I would be surprised if it's broken on any even older SBCLs than that. Although if you go too far back, I'm sure something else breaks.
Right.
1.4.8.
Yeah, 1.4.8 definitely works.
1.4.8 definitely works. Okay.
Yes.
So
that's the one that I'm using right now, and it works for me at the very least. And I can reproduce the bug that causes it to break on 1.4.10. So, as far as I can tell, it's SBCL version specific.
Interesting.
But yeah.
Are there any more questions from the audience?
I realize this is a lot of stuff really fast, but
I know it's a bit overwhelming, but if there aren't any more questions. Next week, I think this would be a good time to start especially this application. Brought on some questions I had, to which I was talking to Elijah earlier about this. Starting next week, I wanted to start actually diving in more deeply into class, and for that, that means we're gonna go into more of a book review phase for the next couple of episodes. The book that I'm suggesting that we go through is actually it's a classic book.
Sonia's book?
Yeah, Sonia's book, yeah. Object-Oriented Programming in Common Lisp, A Programmer's Guide to Class. It's a small book, but it's a fairly dense and very involved book detailing some of the features. And to really get into some of the other more advanced features of Common Lisp, like the meta-object protocol, we need to cover this foundation a little bit more in depth and see what's available.
A lot more in depth.
Yeah, a lot more in depth. Yeah, along with a few episodes on macros. For that, there's another.
Wow, WA's the guy with the cat icon in her in our stream right now. He was wondering about object-oriented programming and Common Lisp this weekend. He was on our stream watching us. So yeah, if you're watching, wow. Check out our stream next week.
Yes, starting next week and the next couple of weeks, we will certainly be having this this discussion, and it sets the stage for a lot of other things as well. I know Baggers in one of his streams gone through macros. I haven't had a chance to really delve into that, but I think we should cover it too as well to give more of a bigger discussion on it. So, but you know, that's in the coming weeks, folks. Starting next week, though, we will be going through this new book, Sonia Keen's book. Again, it's called Object-Oriented Programming in Common Lisp: A Programmer's Guide to Class. It is available on Amazon. You could probably, there might be something out in the open internet, but I'm not going to recommend that. I recommend you getting the actual paper copy because it is a nice book. But we'll start that next week. So if there's nothing else, I'll see you guys, next week.
Sounds good to me.
See you guys. Bye.